going back the other way. Well, we saw yesterday that when we differentiate sine, we get cosine. So therefore, logically, if we integrate cosine, we'll get sine. Notice I've put a linear function there rather than just function x. So we would divide it by a. Sine, and this is where we've got to be careful, because we're going back the other way, the negative ones very often we can get wrong. Because when you differentiate cosine, you get minus sine. Therefore, when you integrate sine, you get minus cosine. So you have to be very careful with that. And then the third one then would be sec squared, because we saw that when we differentiate tan, we get sec squared. So they're the standard sort of integrals that you get on the formula sheet. But it only has a linear function. Again, if we think of it with the idea of I want to create the derivative out the front and then the derivative of the angle for those other type of ones. So let's just have a look at some. So if it is a linear function, terrific. I'll just go 1 divided by the coefficient of x. So in this case, it'll be a third, but sine will go to negative cosine. So minus a third cos 3x, plus, of course, a constant. Again, that's a linear function, and you'll see the vast majority of questions we get will be linear functions. So minus 1/5 will go out the front, but cos goes to positive sine. So it will be minus 1/5 sine of 1 minus 5x. And there's a sec squared one. It's also linear. Turn a half upside down, we get 2. So we'll have 2 tan x on 2. All right, let's do a definite one. Sine 2x. So that'll go to minus a half, because sine goes to minus cos. Radians. Whenever we're dealing with calculus and trig, radians is the angular measure. So we're going from pi on 6 to pi on 2. So let's sub it in, and we get, well, I factorised out the minus a half. Cosine of pi minus cosine pi on 3. Oh, let's think of the graph. Cosine pi, we start at 1. So pi, we must be down at minus 1. Pi on 3. I don't know about you, I still convert these into degrees to work out the exact value. Pi on 3 is 60 degrees, and the cos of 60 is 1/2. So we've got minus 1, minus a half, all of that times minus a half, 3/4. Let's do a volume question. So we're going to find the volume of the solid when y equals the square root of sine pi x. All right, let's find the volume. Pi times integral of y squared dx. The main reason, I guess, I made the curve y equals the square root is because I knew we were going to square it, and then it makes the integration rather easier. We're just integrating sine of pi x there between 0 and 1. Integrate sine, we get minus cosine, but 1 over the coefficient, which will cancel with the pi out the front. So there's our minus 1 on pi, which will cancel with the pi. And we just got cos pi x from 0 to 1. Cos of pi is minus 1. Cos of 0 is positive 1. So we got minus of minus 1 minus 1. Positive 2 units cubed is the volume. I can see why you were so concerned about that. That was very tricky. Yes. Yes. Right, here's one where the function is not linear. This is what I was saying. Same idea that we did for log functions and exponentials and that derivative times function to the power of n. Let's try and create the derivative. The derivative of the angle would be 2x. We've only got 1x. So that's easy to fix up. We'll multiply by 2, but then to balance it out, we'll have a half out the front as well. So 2x sec squared x squared will just go to the tan of x squared. And then, of course, we've got the half out the front. Uh-oh! Sine squared. Now, cast your minds back to last year when we were doing trig functions, and we learned our double angle results. And I said, Look, cos 2 theta, we can write it in 3 different ways. And actually we can rearrange them. And this will come in very useful next year. But you might forget. Well, it's now next year. Did we forget? Sine squared, what is it?
1 minus cos 2.
So close. Half of 1 minus cos. So we change our sine squared. Remember, cos 2 theta could be cos squared minus sine squared. But then we could change it to 1 minus 2 sine squared, which means sine squared is a half of 1 minus cos 2 theta. And the other one, if it was cos squared we want to integrate, notice they're very similar. It's just that the sine squared is 1 minus cos 2 theta and the cos squared is 1 plus cos 2 theta. They love asking somewhere in the paper, whether it's involved in an actual question or just a question by itself like this one, they love asking the integral of either sine squared or cos squared or something to see if people remember that one. So I'll guarantee somewhere along the line we will come across this type of question. All right, so let's change our sine squared. Half of 1 minus cos 2x, and now we've got something we can integrate. Integrate the 1, we get x. Cos goes to positive sign when we're integrating. So we do 1 over 2, and there's our final answer. I've expanded it out. X on 2 minus a quarter sine 2x. Integral of tan x. Who remembers from yesterday? Close. Very close. Oh, close. Let's show you. The way we work it out, remember, tan can be written as sine on cos. I now have a situation of derivative on function, almost have that situation. Because, of course, the derivative of cos x is minus sine x. So I can fix that up. I now have derivative on function. So it's minus log cos x. You said log of minus cos x. So it was close. That's one way you could write it. If you don't like negatives, and I'm a bit like that myself, to be honest. Remember, with logs, we can bring the power in. Cos x to the power of minus 1, or the reciprocal of cos, I could write it as the log of sec x. So it keeps it positive. Doesn't really matter, but either one. That is not on a standard integral sheet or the formula sheet they give you, but it is well worth remembering. You don't have to go through deriving this each time. You can just go, integral of tan, right, that's the log of sec. And just write it down. There'll be other ones like that. Certainly in our Foynian integration, when we start looking at that, ones that aren't on the standard integral sheet, but do crop up quite frequently. And so they're worthwhile just knowing to save time. Ooh, here we go. Cos x sine to the power of 7. This is actually one of our ones where we want to create the derivative times the function to the power. So the function to the power, the function is sine x. The derivative of sine x was cos. So we actually have it. It's already in that form. Derivative times function to the power. So all I've got to do is add 1 to the power of the power. If you did it via that substitution way, which we'll look at more detail later, you could do it this way and it might become a bit more obvious. You say, oh, well, let's let u equal sine x. So du would be cos x. But I'd need to change my limits in that case. And I'd just end up with that. And so there's minus an 8th u to the power of 8. Sub it in. Personally, I wouldn't do that. Personally, I would look at that and say, hey, it's in the form derivative times function to the power. So I know I just add 1 to the power over the power. And so it would become sine to the power of 8 over 8. And then sub in the 0 and the pi on 2. I just think that is quicker than using the substitution. So if you recognise it, great. If you don't, well, then we have other ways of coming up with solutions. Alrighty, that'll do us. 14I, 14J. All right.